First of all, welcome to my talk. My name is Irina Heinz, and I'm a PhD student at the working group of Guido Burkhardt at University of Constance. And I will talk about our work that we recently put on arXiv about a crosstalk analysis for single qubit and two qubit gates and spin qubit arrays. And as you already heard in the talk, in the previous talk from Menno, we're thinking about scaling up spin qubit devices. And if we want to operate a qubit, as shown here, for example, then we will never have perfect isolation to the surrounding. And this will cause an effect on the neighboring qubits, which is indicated by this arrow. And this is called crosstalk. So this is the case for single qubit and two qubit gates. And we focused here on the Y and the CNOT. Okay, so first of all, here are the devices that we are looking at. So we have these gate-defined quantum dot structures, and each of these quantum dots is then filled with one electron. And then we want to, or this electron has a spin, and the spin is our representation of a qubit. So that means that we want to manipulate this the spin to operate this qubit, and this can be done by in a magnetic field. And there are two ways to do so. So we have the first way, like as you already saw in Menno's talk. So we have the global strip line where we can run or apply a current through a strip line, and this will cause a magnetic field around this, and this will cause the qubits or the spin to be manipulated. And there's another one, it is the EDSR, so this is quite similar. We embed this gate structure within a magnetic gradient field, and if we now apply an AC voltage here, this will cause the electron to wiggle along this gradient field, and this will cause an effective magnetic field. So as you already see here, like in this device at the right, where we have 4 quantum dots, so 4 electrons, we see that we will always have an effect on each of these quantum dot, each of these qubits, and this means that we have to look at crosstalk effects. So we were looking at this such a scheme of a gate-defined quantum dot, where we have these middle barrier gates which can turn on and off the exchange interaction J, and then we can describe this whole system with a Heisenberg Hamiltonian. So here we assumed for the first time that we are in silicon, so that means we have no spin-orbit interaction, but in principle, the ideas that will follow from now on are applicable to any device that suffer from crosstalk in spin qubit devices. So we have the Heisenberg interaction here with this exchange interaction, and we have the gradient or the magnetic field that enters with the gradient fields. So these are both gradients, and the effective magnetic driving. And if we now have the Hamiltonian, that means we can also define our time evolution. And this time evolution can be compared to the real gate that we want to apply. That means we can compare the gate evolution to the actual evolution within the gate fidelity. So the gate fidelity is our quality measure, and this is what we were looking at. Then we looked at single qubit gates, and therefore we picked the Y gate. So the Z rotations can be implemented via software. So we were looking at the Y gate. And here we assume that we have a qubit 1, with resonance frequency BZ1. And now we apply a Y gate with a driving strength of BY11, matching this resonance frequency. And then we have a neighboring qubit 2, with resonance frequency BZ2, which differs from the first one by this delta BZ gradient field. And on qubit 2, there will act a rest field of the driving. So this is determined by this alpha here. And we will, and then we look at the fidelity of the second qubit. So this is what we are interested in. We want to look at crosstalk and not at the whole gate. We here assume the gate is already fully optimized. So we look at the neighboring qubit. And this is what we get. So we have the fidelity depending on our gradient field, which is this one. And we see that the fidelity increases for larger gradients, which makes sense due to the fact that the transition frequencies of the two qubits further differ. And so we get a higher quality of this operation. Then we have also the fidelity, which can be plotted against the driving field, which is this one. So, and we see that the fidelity decreases here. And this also makes sense because if we increase this driving field, we also increase the rest field that acts on qubit 2, and this will cause a larger effect on qubit 2. And so we'll then have a larger crosstalk effect. Okay, so we can do the same for 2-qubit gates, and therefore we looked at the CNOT gate. And to do so, we switch on the exchange interaction adiabatically between qubit 1 and qubit 2. And then we drive with a driving strength of B drive and matching the resonance, the transition frequency of the CNOT gate. We drive these both qubits. And what we are looking at is qubit 3, so the neighboring qubit, which has a resonance frequency BZ3, which differs from the single qubit resonance frequencies, again by this delta BZ gradient. And we have a rest field also given here by this alpha. And we see the same result. So we have the fidelity depending on our gradient field, and we see the same. So the fidelity increases for higher gradients. That makes sense due to higher or to further deferring of the transition frequencies. And the fidelity, depending on the driving strength, again decreases for higher drivings due to the fact that we have a larger effect of crosstalk here. Okay, so now crosstalk is an effect that we don't want to have. So this is unwanted, and we want to find a way to avoid this. First of all, let's look at our Y-gate again. To perform a Y-gate on this first qubit, we have to perform a pi rotation. That means, or in general, 2m plus 1 pi rotations. And then we can look at the second qubit. What does the second qubit do? And what it does is what you see here in this block sphere representation. So here the state evolves within such off-resonant Rabi oscillations. That means so oscillations around combined axis, two combined axes. And what we can do now is we can find a driving strength such that we stop at exactly this, or the driving time matches exactly such that it stops at the initial condition, so in the initial state. That means we perform here a 2 pi k rotations on this second qubit, and we can then derive such an expression for our driving strength, which is dependent on our alpha. And now we can look at the fidelity again. So the fidelity, depending on our driving strength, which is given with the blue line here. This is the fidelity we saw before. And indeed, if we now look at the synchronization conditions, which are given by these vertical lines, we see that the fidelity gets maximal. And if we now further apply Z rotations afterwards, we can even take this fidelity to 1. That means we have no crosstalk at these points. This is all done within the rotating wave approximation. Okay, then we also can think about if we have not only one neighbor, but 2 or even more. We just looked at 2. So what happens if I drive a qubit and I have a neighbor on the right and on the left, and with different driving strengths, so different couplings, alpha 1 and alpha 2, due to the fact that, of course, architecture is not perfect, and we have probably different couplings. For that, we can derive two different synchronization conditions, and now we want to fulfill both of them. So we have 3 parameters, k, m, and l, which are integers. And if we now decide alpha 1 to be 0.4, we see the following. So here we have the alpha solutions for alpha 2, and here is L, k is set to 1 for different m's. That means we have only discrete solutions for alpha 2 such that we can synchronize both of these neighbors. That means it's not possible in principle to synchronize both of these neighbors for arbitrary alphas, but we can choose a combination of L, K, and M such that we find such a point close to our alpha value, which also reduces in the end the crosstalk effect. Then we also looked at the noise analysis. So what happens if we include noise in our analysis? That means we here look at the noise that comes from our driving. That means our driving is electrically driven, and this will cause fluctuations also in the magnetic driving strength. And this is what we see. So these are our results. If we plot now the fidelity without noise minus the fidelity with noise, so what you see is the overall contribution of noise to the fidelity depending on our driving strength. Then we see the following. So we have the minimal contributions of our noise to the fidelity close to these vertical lines, which indicate the synchronization condition. Here we assume the Gaussian noise, and this is quite convenient because that means that if we fulfill this synchronization condition, we are also kind of less sensitive to noise. And then, of course, we can think about what happens if we drive single qubit operations at the same time. So if we now looked, for example, at this algorithm, this is from the Google paper, and we see that we perform single qubit operations at the same time here in this circuit. And then we also want to think about, okay, how does this crosstalk effect looks in these simultaneous driving? Therefore, we looked at qubit 1 and qubit 2 driven simultaneously with different driving strengths. Here, this crosstalk effect is symmetric in our case, and we drive a Y gate here. And I won't go into detail too much here at the slide, but so this fidelity here, this is the fidelity depending on the driving strength of the second qubit. And here we already optimize the condition for the first driving as much as we could. And what we see is the following. So we have the fidelity of qubit 1, we have fidelity of qubit 2, and we have the total fidelity of both of these qubits. And what we see is even for the highest optimization that we find, we will still have an unavoidable crosstalk effect here. So the red line is the total fidelity for both qubits, and we see that it will have an unavoidable effect, and this for optimized conditions already. So what we can do here is, if we think about like a linear array, so a 1D array, we can think about a 3-step synchrony or simultaneous driving. That means we first of all start with qubit 1 and qubit 4, and then we continue with qubit 2 and qubit 5, and the third step we drive qubit 3 and qubit 6. And in each step we can synchronize one neighbor. That means one neighbor is completely completely crosstalk free, and the other neighbor we can synchronize almost or nearly, and this means our crosstalk effect is reduced here. And this can be done for each step, and this will reduce the overall crosstalk effect in this driving. And the nice thing here is that we have a fixed factor of 3 that will scale our driving time. Okay, so let me conclude my talk. So what we found was, first of all, we can now quantify the fidelity for a neighboring qubit which suffer from this crosstalk effect. And then we looked at schemes how to increase the fidelity. That means how to avoid this effect, this unwanted crosstalk. And then we also found out that the synchronization condition we got is not only good for an ideal gate operation, but also robust against charge noise, which is quite convenient. So with that, I would like to thank you and open up for questions.
Thank you very much for the nice talk. Indeed, the talk is open for discussion, and Florian Ginzel has a question in the chat. Can you give some details on the noise model you used for the robustness part of the talk?
So I use Gaussian noise. So in fact, this is a very simple model for that. I just use a Gaussian noise with different standard deviations.
So Gaussian noise on the on-site energies of the dots, or on some electric field which is pushing them back and forth, or
on the driving field. So that means on the rest field of this on the second qubit. So these are the the noise contribution here.
So physically, what does that correspond to?
These are the fluctuations within the ESR driving strip line, or also if we drive with EGSR, the charge noise within these this driving of a qubit.
So Menno mentioned these charge traps which are fluctuating, causing this 1/f noise. Could that also be a reason for this term in your Hamiltonian?
Sorry, again, I didn't get it.
Menno mentioned these fluctuating charge traps, which he believes causes this 1/f charge noise in his SET and quantum dot devices. So is that also, can I also think of that as being incorporated in this sigma BY12, or that's something completely different?
Yes, I think this is something that we could think of. I don't know now the noise spectrum of that exactly, but if this is kind of if we can model this with the Gaussian noise, then this is included within this.
There is a question in the chat. Devdut Sharma asks, can we increase the coherence time of the qubit? I let you interpret the question first. I'm not sure what it means.
Okay, this is difficult to say because I'm looking at the crosstalk. That means I'm not looking at the this is an effect that is not caused by any dephasing processes or decoherence processes, but this is an effect of the actual driving. So this is pretty much not the main source of coherence. So this is why I cannot answer this question in this sense.
I have one more question. So as far as I understand, there have been at least one experiment doing similar things, like having a micromagnet, doing EDSR on 2 qubits. This is Thomas Watson and co-authors, 2018. And I'm just wondering, I mean, did they use any of these techniques which you introduced here to make their, because these crosstalk effects are there in the experiment, I'm sure. So did they use similar tools to make a more precise 2-qubit quantum processor, or they disregarded these crosstalk effects? Do you know that?
Actually, I don't know. I think in this paper, I don't know if it's really in this paper or in a cited paper. They looked at the crosstalk effect, but they just drove these 2 qubits at the same time and then looked at the crosstalk effect. I haven't read something about optimizing this crosstalk effect.
Good. Maybe one more question. So it would be natural to incorporate like phonon effects, for example. Do you think they would, I mean, do you think they would matter, or whether they would matter, does that depend on which material you describe? It's actually another question. So which material is this model suitable for?
I think we started with silicon, and we neglected the valley splitting here. But in principle, if we can measure the Rabi oscillation frequencies, then in principle it is possible to do it with every kind of material, because what we do is just synchronizing these frequencies, and this is the main point of this crosstalk effect. So I think this is suitable for many devices that is not that material specific.
All right. Thank you very much for the talk and also for the responses to the questions.